So today I want to go through our NMR example, and here we've classified it as NMR1. Now before we continue, it is essential that you've already gone through and have an understanding of the 1D and 2D NMR lectures that are represented on CAIR's website. So what are we going to be able to understand during this talk? Well, we want to understand the relationship between 1D and 2D spectra. What we're also going to look for is some of the downfalls of some spectra and how other 2D NMR experiments can help you with this understanding. And the ones that we're going to cover today is what is deemed to be one of the most essential for understanding structural lubrication, which is Cosy, HSQC and HMBC. What you are going to see in the following slides is real-life examples. Sounds almost like a movie thing, but real-life examples. And there are downfalls to them. I want you to note and watch out for them and see how we start to divulge into these downfalls and try to use other spectra to help with this understanding. So the example that has been chosen today is fluconazole. Fluconazole is a well-known drug, and I'm not going to go into the details about to which its medicinal purposes are, who made it, etc. For now, we want to be able to just look at its structure and spectra. So here is a 1D NMR of fluconazole. What do we want to know about this spectra? So first of all, we want to be able to understand how many protons add up to each one of the signals. And this is known as integration. Where can we find integration? Integration are the numbers that are present below the spectra that you can see here. And what do? Well, what we do is we start to round to the nearest whole number to determine how many protons are making up that signal. So we've taken this one peak here, which has a value of 1.93. So if we were to round this number up, it's 2. So we can therefore say that 2 protons are equating to this signal. And how should we start to write this or annotate this on our spectra? Here, we just write H1 and H2. Now you're thinking to me, well, hold on a minute. What happens if it's a CH2? Then technically it's H1 and H1 prime. Well, we don't know that yet. We want to start to be able to use all of our knowledge to be able to fully understand what it is that we have in front of us. So if we were to do this integration to all of these peaks on the spectra, we start to see that we have we have 12 protons in the spectra. What are the next things that we want to be able to understand? Well, we now want to be able to understand the regions in the spectra. And what I mean by regions is, where do things fall in relation to functionality? We know from previous talks that aliphatic regions are about 0 to 3 ppm. Aromatics, for instance, are about 6 to 9 ppm. And what we want to be able to look at here in our spectra is, well, what is our spectra telling us? Our spectra, first of all, is telling us that we have a large set of aromatic peaks, 8 of them in total. And we have something that is falling either as an aliphatic or something that is potentially heteroatoms, for instance. What else do we now want to know? Well, we now want to be able to understand peak shapes. And what do I mean by peak shapes? I mean by which things start splitting. They're telling us how many neighbours something may have. So what we do is we'll take this first example. Here we have 2 sets of doublets. Using this n+1 formula, we can say that because it equals 2, that n, which stands for the number of neighbouring protons, is therefore 1. So we can say that each one of these peaks has 1 neighbouring proton. Now we want to take everything into consideration, everything that we already know. Integration, for instance. We know that each one of these peaks equates to 2 protons, but we know that each one of these peaks therefore has 1 neighbour. What region does it fall in the NMR? It falls in either something that is attached onto an electronegative element or something is itself electronegative. So, what does this equate to in fluconazole? Looking at the structure of fluconazole, we are ideally, first of all, looking for a CH2. And here we have 2 sets of them, with one of them being highlighted on this diagram. It says here that there is 1 neighbouring proton. So when we actually look at this CH2, we go, okay, let's try and find that neighbour. We look down towards this nitrogen species and realise that there's no proton attached onto it. So it can't be this. We then look in the opposite direction and we see a quaternary carbon. quaternary, meaning it's not going to have a hydrogen atom attached onto it. So we say, well, where is it getting this neighbouring from then? Because in theory, it should therefore appear as a singlet. It doesn't have any neighbours. But what we said before about some NMRs is that the ability to detect geminal and vicinal coupling. Vicinal meaning neighbouring, geminal meaning attached onto the same carbon. And perhaps maybe what we are seeing here is geminal coupling. But we want to use further NMR experiments to help us make that conclusion. So let's now look at another peak. Here we have sets of singlets, and by meaning of singlets, it contains no neighbouring protons. What do we know about these singlets? Well, they fall within the aromatic region. So we are looking for hydrogens or protons that are connected onto an aromatic species that do contain no neighbours. So we look at our structure, and we see that there are two sets of triazoles and one substituted aromatic ring. Taking the triazoles into account, which we've highlighted here in green, you can see that these green protons do not contain any neighbours, and looking at a 1D NMR spectra, they should appear as singlets, so perhaps these are them. However, I said you had to take everything into account. Now, an aromatic proton can only be one, as in the sense of it integrates to one. And why is that? An aromatic carbon can only contain one hydrogen species on it. So if we look at integration here in the aromatic region, why do we see two protons? We're looking at it and we're thinking, okay, there's two protons here, but I can only technically have one proton attached onto an aromatic carbon. It contains no neighbours. Do I have some form of symmetry in my molecule then? That these two protons are identical, they're in the same chemical environments to one another, and the NMR can't distinguish the difference, but they still also contain no neighbours. Looking at the structure of fluconazole, we have two identical triazole rings, so perhaps what we are seeing here is two protons, one from each of the rings. But again, we want to use some further experiments to help us determine that conclusion. Something as well that is of great use as well is this other aromatic set of protons, 3 of them in total. What are they? Well, we have one remaining ring that we're not really too sure about, or we haven't actually started to look at yet. What do we know about these? These are splitting into multiplets. There are 3 protons, like I said to you, equating for them, but with one of the multiplets appearing to have 2 protons associated with it, protons 5 and proton 6. We're then saying, okay, what can this tell us about it? Well, for now, we want to leave it as it is. We're just saying that there's 3 aromatic protons. We're not too sure what and how they see, because perhaps some of these see these, perhaps these both see each other. Right now, we don't know. What we could do is that we could divulge into the J coupling and blow up these peaks and measure the coupling between them, and perhaps maybe find the distance between these 2 protons and being able to say which peaks are able to see one another. However, in this example, I want to also incorporate 2D NMR, so for this purposes, I'm not going to divulge into that. However, it is a technique that you should use when understanding your 1D NMR spectra. So let's start looking at some of these 2D spectra. Let's first start looking at the Cosy spectra. Again, not going to go into detail about it, but the Cosy spectra is a correlation experiment between neighbouring protons. How do we first start to look at a Cosy spectra? We first of all start to look at the diagonal. And what we are most interested in as the Cosy is the cross peaks. The cross peaks are telling us where potential coupling is happening. And what do we first of all want to do? Well, we want to start studying what protons can see each other. So taking the first example here, that we can now see that protons 5 and or 6 can see number 7. So this is now telling us that these 2 sets of peaks can see one another. Which proton, because remember there's 2 underneath here, can see number 7, again, we still don't know this. What else do we know about the spectra? Okay, so we look at the next set of coupling, and we can see here that protons 9 and or 10 can see 11 and or 12. Okay, that's something that we've speculated before. We knew that perhaps they could see each other, but now this is now confirmed in the Cosy experiment. What now can the Cosy tell us? The Cosy now tells us as well that protons 1, 2, 3, 4 and 8 are all Cosy silent, which means that there is no coupling taking place. So it's good to see a good correlation between the 1D as well as the Cosy experiment. We already knew there was coupling between these two, or these sets of peaks here, and we knew that because of the singlets that there was no coupling, but it's always nice that this has been confirmed in the Cosy experiment. So where do we now want to take our 2D experiment? Well, we now want to start to say is, okay, I want to know direct coupling, and what I mean by this is I want to start to understand which proton is connected onto which carbon species, and to do that we need to use an HSQC. In very brief, a HSQC does not have a line of correlation because on one axis we have a 1D proton experiment and on the other axis we have a carbon. So HSQC is a heteronuclear experiment. What do we want to start to take from this piece of information? We want to start to look to see, well, what carbons are there in my spectra? So the first thing that we notice is that for proton number 8, if we are to look down on the spectra here, we don't actually see any peak being represented at all for this proton. And because of that, we can make the suggestion that perhaps proton number 8 isn't associated with any carbon, and perhaps it's actually a proton that's connected onto something that this spectra can't see, such as a heteroatom. Now again, because we're fortunate we have the structure of fluconazole, perhaps it could be this OH species here. Moving on from this, when we start to actually look at the HSQC, remember we read down and across to the carbon species here, that we can see that all of these peaks that we've just highlighted here are all associated with aromatic carbons. And how do we know that? Because they all fall within the aromatic region of the carbon spectra. What it should be noted is that when you are understanding or interpreting an HSQC, what its key is that you write down the ppm shifts of those carbons, or you give those carbons numbers. So for instance, the green one that is highlighted here, that we can see here, we can say that this is carbon number 1 and carbon 2, because this is proton 1 and proton 2. In the blue example, we can then say this is carbon number 3 and carbon number 4, and so on. What else do we want to be able to interpret from this HSQC? Well, looking at this HSQC, we have on the purple here that 9, 10, 11 and 12 are associated with the same carbon. Now, because remember we looked in the 1D experiment and it said that these integrated for 2 each, so meaning there's 4 protons in total, we can't have a CH4. Well, we can, that's methane, but then that would be the structure over. So it's not that, it's 2 sets of CH2s because they are coming off in the same shift. Because of that then, we then say, okay, perhaps they are identical CH2s. And again, this is where it comes into, do we have some form of symmetry in our molecule? Now, just looking at the structure of fluconazole, again, we have these 2 identical CH2s. So perhaps one set is from one and the other set is from the other. So this is as much as we can take from the HSQC. The HSQC is confirming what we've already speculated, but it's helping us now, for instance, understand that we have some sort of geminal system happening here. So this is telling us that there is a CH2. Going a step further, we want to start to look at, well, we've understood how a Cosy spectra works, so the coupling between neighbouring protons. We've now looked to see which carbon is associated with which proton. And now we want to understand, well, let's start to build a map in our heads. How do we start to link all of these things together? And we can use what is known as the HMBC experiment, which is a heteronuclear multiple bond coherence experiment. And it's read exactly the same as an HSQC. You work your way from your proton and you figure out to which carbon signal it is being able to see. So in this spectra here, black is indicated by the HSQC and red is indicated by the HMBC. I would always advocate that reading an HMBC is always good practice to overlay your HSQC because it offers an awful lot of understanding to the spectra. So what's the first thing we want to start looking at? Well, let's maybe take a look at these peaks down here. What can we say? Well, protons 1 and 2 and 3 and 4 look to be potentially 3 bonds away because the HMBC can see roughly 3 bonds away, 2 to 3, but roughly can see 3 bonds away, which is good. So we've worked our way from the black and we've worked our way till we see a HMBC signal which is located here. How do we know what this one is? Well, there's the black line there. It's telling us that these see each other. So let's start to work again. Now we're going to look at the peaks 9, 10 and 11 and 12. And we've said here that they can both see each other. So looking here, you can see the black for the HSQC, but underneath, particularly this one, for example, as well, you can actually see a hint of red, indicating that these can both see each other. Now remember, a HMBC can measure typically 3 bonds away. So what does this look like? We said that these look to be CH2s. The Cosy and the HSQC confirmed this. But because the HMBC is saying that they can see each other, it suggests that they're not next to each other, but they are separated by some sort of atom. Now what this atom is, it could be a quaternary, it could be a heteroatom. Right now, we don't know, but we know that there's something potentially separating these two. What else can we say? Well, that these CH2s can see peak number H8, so proton number 8. We said before that proton number 8 looked to be some sort of heteroatom. So is this heteroatom in the middle? Again, we're having to speculate and see. We can also say that these CH2s can also see sets of quaternary carbons. And how do we know they're quaternary carbons? Well, the ones that we've highlighted here is the reason being there's no black dot on this line to signify that there's any coupling taking place between something that already contains a proton on it, suggesting to us that these are therefore quaternary carbons. Proton number 8 is also sharing this coupling between this quaternary carbon. What else can we say about this spectra? Well, H1 and 2, 3 and 4, we already determined could see each other by this coupling happening here. But what else can we say about this spectra? Well, actually, the CH2 is close to it because the CH2 can actually see this aromatic peak here. So, what does that actually look like when we're looking at the structure of fluconazole? So here, we determined from our 1D experiment that we have some aromatic peaks, and these aromatic peaks look to be 1, 2, 3 and 4. We said already that these aromatic peaks contain no neighbours, that they were on their own, and this is here represented by this diagram that we can see here, that 1, 3 and 2 and 4, because right now we can't distinguish the differences between these. What I've done is 1 and 3 because one set and one set, because 1 and 2, they are the same carbon but on different rings. Looking again, 9, 10, 11 and 12 we said was a potential CH2, and again we can't determine the differences between them, so perhaps maybe 9 and 11 are part of the same, and 10 and 12 are part of the same. Or perhaps 9 and 10 are one of these, and 11 and 12 are one of these. But right now it's making us difficult to make that conclusion. So let's take a look again. So this is just looking at it from fluconazole's point of view, as in its structure. Here I've labelled the structure and only taken part of the molecule that we're interested in explaining. The black line is indicated by 1 coupling length, the red is indicated by 2, and the green line is represented by 3. And this is present on all these. The red boxes around it is referring to the red box present on the spectra, and the blue box is referring to the blue box around the structure here. So what do we want to now say? Okay, we have 2 sets of quaternary carbons here, and it is shared by the CH2s as well as this potential heteroatom. So how does that actually look? Here, we have an aromatic carbon because it falls within the aromatic region. So looking at the structure of fluconazole and counting for, let's say, the CH2 at least, let's count the bonds. 1, 2, and 3 to be able to reach this quaternary carbon, and I've indicated it as being in green. When counting for the heteroatom, so the OH for instance, in fluconazole, we count 1 bond is to the oxygen, 2 bonds is to the quaternary, and 3 bonds is to this aromatic peak here. So we can say that this chemical shift that is present here is accounting purely for this quaternary carbon that is present here, so the substituted aromatic ring. When looking here at this one, we can then say, okay, well, what's this quaternary carbon then? We need to start counting that too. We can say that just by looking that the carbon spectra, it's some form of aliphatic peak because of where it falls in the carbon spectra. So again, we can start to do our counting and realise actually that this is accounting for 2 bonds away, 1 and 2, because here is the quaternary carbon that's aliphatic. Going in the opposite direction, we're hitting aromatic peaks here. So this is the quaternary carbon. So remember I said to you before that the HMBC can measure 3 bonds away, but it is optimal and it's set to read at about 10 Hz, which is approximately 2 to 3 bonds. So let's now look at the blue structure here. What can we determine from this? The CH2s can only see one set of aromatic peaks, an aromatic peak that is associated with this triazole ring. But which one? Which one can it see? What is this carbon signal here? So looking at the bonds again, black, red and green, going in this green direction here for 3 bonds away, you end up on this nitrogen atom that doesn't contain a hydrogen on it at all. Now that's okay, because a HMBC can measure quaternary elements, but because nitrogen in the HMBC that we measured was a proton-carbon correlation, this means that this cannot be seen in the HMBC. Going in the opposite direction, here now we reach a carbon attached on to a hydrogen species, evident here. So we can therefore say that this carbon that is here is actually this carbon on the triazole ring, which means that this one, because it is not seen by the CH2, is the one that's furthest away, which is the one that is present here. So what are the conclusions of what we've learned? Well, we did manage to be able to determine the structure of fluconazole, and we're able to assign each of the carbon peaks and the proton peaks to that structure. But how did the experiments help us? The HSQC was key to being able to understand that fluconazole had perhaps geminal coupling, and that the Cosy identified this coupling. The HMBC was a very, very powerful experiment. Why? Because it was able to identify the quaternary carbons, and not only that, but make the distinction between which of those aromatic proton 1, 2, or 3 and 4 was where it was on that triazole ring. You also notice as well that the carbon spectra was unbelievably weak. There was high background noise that you saw on it. However, the HSQC and the HMBC made up for this downfall. The HMBC was able to see those quaternary peaks, which are often very, very weak in a carbon spectra anyway. The HMBC, though, had another one of its downfalls. Because it was measuring a proton-carbon coupling, it could not detect the coupling to nitrogen, but also note as well that HMBC can be run with a proton to nitrogen coupling. So you can see here that all of the information, the 1D, the Cosy, the HSQC and the HMBC, all enhance the power to be able to understand the spectra and the structure of fluconazole. This talk was brought to you by WCAIR, Scotland, UK.